Hi, this is Geometry, Lesson 1-4, Inductive Reasoning. In this lesson, we'll be able to use inductive reasoning to make conjectures about mathematical relationships. Our lesson vocabularies are conjecture, counterexample, and inductive reasoning. So we'll learn what they are. Let's start with explore and reason. When points on a circle are connected, the line segments divide the circle into a number of regions, as shown. So if you look at the figures, we start with one circle, and then we have different chords that divide each section. And so on the second circle, we have one chord, and then we have two sections. And then the third circle, we have 1, 2, 3 chords. We have 1, 2, 3, 4 sections. And then the fourth one, how many chords do we have? 1, 2, 3, 4, 5, and 6. 6 chords. And how many parts, how many sections do we have? 8. So how does the number of regions change when another point is added? So if you look at the points, we have 1 versus 2 versus 3 versus 4, right? If we look at them in terms of points, each point is added, but sections are not being added by 1. So what are the patterns that we see here? So besides the number of points or the number of regions, we could also count the chords that are drawn or count the number of regions that are bounded by part of the circle. So we can say that for each new point on the circle, the number of regions doubles. There's 1 region, there's 2 regions, there are 4 regions, and then there are 8 regions. So each time a point is added, the number of regions doubles is the pattern that we see, right? So let's record that. For each new point on the circle, the number of regions doubles. Alright, let's look for relationships. Using the pattern you observed, make a prediction about the number of regions formed by connecting 5 points on a circle. Make a drawing to test your prediction. Is your prediction correct? So we stopped at 4 points. How can we predict how many regions we'd have for 5 points? So what would be the next circle here? Can you predict? Can you make a prediction? Yeah, by this pattern, we can say 8 times 2, 16. So it's going to double the amount of the previous circle's region. And so we can predict that we would have 16 regions in the next circle where it has 5 points. So let's try to draw and see if that's correct. See if our prediction is correct. So this could be our next circle. We can add another point. 1, 2, 3, 4, and 5. So then 1, 2, 3, 4, 5, 6, 7, 8 different chords, 9 different chords, 10 different chords. Okay, and then we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And yes, it exactly doubled up. So yes, we can predict that a circle with 5 points will have 16 regions. And our prediction was correct, as shown on the left. So think about this essential question. How is inductive reasoning used to recognize mathematical relationships? Start with example 1. Use inductive reasoning to extend a pattern. What is an inductive reasoning? Inductive reasoning is a type of reasoning that reaches conclusions based on a pattern of specific examples or past events. So you need to know some information before you make a prediction for inductive reasoning. How can you use inductive reasoning to determine what appears to be the next two terms in each sequence? So looking at the pattern and observing the pattern from the past events or the data we see here, we can predict the next term. So test whether the pattern continues with subsequent terms. What is the pattern we see in part A? 88, 82, 76, 70, 64. First pattern we notice, it's reducing. The number is getting smaller and smaller. But how smaller is it getting? Every time, for each term, we're subtracting 6. So 82 minus 6 is 76, 76 minus 6 is 70, 70 minus 6 is 64. So yes, the pattern continues, and the rule works. Use the pattern to find the next two terms. We can say 58 and 52 would be our next two terms using the same pattern. If we have the same pattern until the last term where it doesn't work, is it the same pattern? No, it has to work throughout the whole sequence. So make sure you test the entire sequence. Part B, 3, 5, 9, 15, and 23. Every time we're adding different numbers, but do we see a pattern? 3 to 5 is plus 2, 5 to 9 is plus 4, and then plus 6, 8, 10, 12, and so on. So we see a pattern with the number that's added for each term. The number that is added for each term is increasing. So by 2, right? So we can use that pattern to predict the next two terms, which is 33 and 45. So now it's your turn. Try number 1. What appear to be the next two terms in each sequence? Try to look for patterns and test if it works throughout the whole sequence and figure out the next two terms. Pause the video and come back when you're ready for answers. Okay, are you ready? So part A, is the number increasing or decreasing? It is decreasing by 200, 200, minus 200, and minus 400, minus 200, and minus 100. So the number that is subtracted for each term is decreased by half. And so the next term would be minus 50, and the next term should be minus 25, right? So 100 minus 50 is 50. 50 minus 25 is 25. So 50 and 25 would be your next two terms. Check your answers. And part B, 18, 24, 32, 128 divided by 3. So did you get the hint? It's increasing by what? By a fraction. So in order to figure out the rational number, you can use the ratio between the two terms. 24 over 18 would be the ratio that increased by, right? So 24 over 18 could be simplified, right? You can divide both by 2 if you're not sure what exactly is the number that divides both of them by the greatest common factor. And then you can divide them by 3. And you see that the simplified expression is 4 over 3. That means 18 times 4 over 3 is 24. Does that work for 24 to 32? You can check. 24 times 4 over 3 is 32. And then it works with that one as well. So 128 over 3 times 4 over 3 will be our next term, which is 512 over 9. And the next term, 2048 over 27. You just need to multiply the common ratio. Yeah, so a lot of times it'd be easier if you find the common ratio or the common difference. But the big idea is that you use reasoning to figure out the pattern and make predictions. Let's look at example 2. Use inductive reasoning to make a conjecture. What's a conjecture? A conjecture is an unproven statement. It's unproven statement or a rule that is based on inductive reasoning. So if it's based on inductive reasoning, is it proven? No, it is a prediction. So in order to prove it, you have to use theorems and postulates. But inductive reasoning, just like figuring out a pattern and making predictions for the next few terms, is a conjecture. In order to prove it, you need more steps. So what conjecture can be made about the number of dots in the nth term of this geometric pattern? So looking at the pattern and using inductive reasoning, can you figure out a conjecture, like a statement that summarizes the pattern predictions that you've made? Right, so here are the term numbers 1, 2, 3, and 4, and the number of dots 2, 6, 12, and 20. The number of columns is one more than the term number, is one observation, and the number of rows is the same as the term number, is another observation. So you can write an algebraic expression to generalize the pattern for the nth term. Every time the term number is getting bigger, the number of dots is also getting bigger by a larger number. So, but the pattern is equivalent to each other. So you can use the n as a variable to represent the number of rows. You have n number of rows, and the columns will always be 1 greater than the number of rows. So the conjecture is that the nth term of the sequence will contain n times n plus 1, or n squared plus n dots, because if you multiply the number of rows by the column, you get the number of dots. Okay? So that is our conjecture using expressions. Let's look at try number 2. Part A. How many dots are in the 5th and 6th terms of the pattern, looking at this pattern? And B. What conjecture can you make about the number of dots in the nth term of the pattern? See if you can answer them by yourself. Come back when you're ready for answers. Okay, so are you ready? Part A, you have number of term 1, and there's 1 dot. And then term 2 has 5 dots. Term 3 has 9 plus 2, 11 dots, right? And then term 4, 16 plus 3, and then it's 19 dots. Do we see a pattern though? If we say we have an nth term of a pattern, right? Well, wait, that's for part B. So what is our 5th term and the 6th term? We can say, we can make an observation that, oh, the number of term is corresponding to the number of rows. Actually, the rows and column without the top part. So these are additional dots we see that are not exactly corresponding to the other dots here that are aligned in rows or columns, right? The rows and columns of the squares that we see are squares. So the dots that we see for rows and columns correspond to the number of terms. You see that? So then you can already figure out a pattern that's 2 times 2 plus 1. That's 3 times 3 plus 2. And that's 4 times 4 plus 3. Do you see the relationship between the pattern and the number of term? Yeah, so the next one would be 5 times 5 plus 4, and the next one would be 6 times 6 plus 5. So the number of dots for the 5th and the 6th terms would be 29 and 41. But can we figure out the pattern and write that as an expression? What conjecture can we make? We say that the nth term of the sequence, so how can we make this as a conjecture? So you see that your nth term is multiplied 2 times, so that's n squared. And then you add n minus 1. The number you're adding is always 1 less than your nth term. You see that? So the nth term of the sequence will contain n squared, or you can say n times n times n minus 1. Or you can rewrite that as n squared plus n minus 1. Okay? Good. All right, let's look at the next page. Example 3. Use a conjecture to make a prediction. Based on the data in the table, how many residents would you expect to vote in the 7th town council election? If you look at the table here, we have town council elections voter turnout. Every year we have total residents count and the voters count. So look for a pattern by comparing ratios between the number of voters and the number of residents for each year. And you can use the pattern to make a conjecture about the number of residents who will vote in the 7th town election. And these are the computations we got. The number of voters divided by the number of residents are approximately 0.11. Okay, so it's about 11% of the total residents. So the number of people who are actually voting from the entire council, the town, is going to be 11%. So using the pattern, you can predict the number of voters on the 7th election, where you know the total residents would be 7,786. 11% of 7,786 could be computed by multiplying that with a decimal equivalent 0.11, which is 856.46. So about 856 people can be expected to vote in the 7th town council election. Okay, so making conjectures would mostly be based on data. You need data to make an inductive reasoning. Let's look at chart number 3. Based on the data, about how many members would you expect the chess club to have in its 5th year? So figure out a pattern like that. Use the pattern to interpret your solution. Come back when you're ready for answers. Okay, are you ready? So every year you get more club members. Do you see any pattern? You might not see a perfect pattern or a ratio. And that's okay. That happens a lot in real life. So from year 1 to year 2, you're adding 3. Year 2 to 3, you're adding 4. 3 to 4, you're adding 5. And so looking at that pattern, we can add 6 and 7 for the next years. Or if you want to find ratio and then figure out how many ratio, like how many percent are we increasing each year, you can use the ratio as well. 13 over 10 is it the same as 17 over 13? Or is it approximately the same as 22 over 17? So you can decide which inductive reasoning you're using and what kind of pattern you're using. But you need to be strategic about that. So the answers could actually vary. You just need to be able to reason it out well. So for example, you can also say, so for example, you can say we're adding one more members from the previous year each year. So then your fifth year could have 22 plus 6 members, plus 6, or 28 members. Okay? All right, let's look at example 4. Find a counterexample to show conjecture is false. Why does a counterexample show that a conjecture is false? Because by definition, a counterexample is an example that shows a statement or conjecture is false. So for example, if you want to prove something wrong, you're going to assume something wrong and prove that's wrong. And then you're going to say, because our assumption was wrong, that's going to be wrong. But counterexample is when you provide a direct example that straight out doesn't go align with your conjecture. So if we have a conjecture that says a polygon with diagonals has 2 fewer diagonals as sides, we can find a counterexample that has a polygon that has a number of diagonals that is not 2 fewer than the number of its sides. Right? So if we have a pentagon here, it has 5 sides and 5 diagonals, and they have equal number, and it doesn't go along with, it doesn't agree with this conjecture. A polygon, and pentagon is a polygon with diagonals, has fewer diagonals as its sides. No, they're equal to each other. So this is a counterexample that says that conjecture must not be true because we have an example that doesn't agree with that. So now try number 4. What could be the counterexample that shows the statement the sum of 2 composite numbers must be a composite number is false? See if you can figure out a counterexample. Come back when you're ready. Okay, are you ready? The sum of 2 composite numbers. What are composite numbers? Composite numbers. By definition, composite number is a positive integer that can be formed by multiplying 2 smaller positive integers. What does that mean? So basically, do you know prime numbers? Yeah, basically composite numbers are the opposite of prime numbers. So if it's not a prime number, it's a composite number. It has other factors than itself and 1. Okay, so 1, 2, 3, they're prime numbers. 4 is a composite number because 4 has a factor of 2, right? As well as 1 and 4. So if it has more than 2 factors, including itself and 1, then yes, it's a composite number. So the sum of 2 composite numbers must be a composite number. So 4, let's say 4 and 9 is another composite number. 4 plus 9 is 13. 13 is not a composite number, it's a prime number, right? So there you go, that's a counterexample. If you figured out another counterexample, great. But you need to figure out 2 numbers that are composite numbers. That makes a prime number to make a counterexample. Okay? So if you have another example, that's fine. You need to find two composite numbers that adds up to a prime number in order to prove this false. So a sample answer could be 4 and 9 are composite numbers, but 4 plus 9 is 13, and 13 is a prime number. So it's a counterexample. All right, let's look at example 5. Test a conjecture. For each conjecture, test a conjecture with several more examples or find a counterexample to disprove the conjecture. So part A, a polygon with 4 congruent sides is a square. So a square has 4 congruent sides and 4 right angles. Is it possible to draw a polygon with 4 congruent sides but not 4 right angles? Yeah. This rhombus has 4 congruent sides, but it has no right angles. So this is not a square. So that's a counterexample for this conjecture. And so it's a false conjecture. Okay? Part B, if a number is a multiple of 9, then the sum of its digits is a multiple of 9. To test the conjecture, list the multiples of 9 and find the sum of the digits of each multiple. Multiples of 9, some of them are 108, 2,817, 9,945, and the sums of the digits are 9, 18, 20, and they're multiples of 9. So the conjecture is true for the 3 cases tested, but obviously you can't test the infinite amount of cases that you can think of, right? So you're just going to say, for the conjecture that we tested, it is true. It doesn't mean it proves it correct or true, but for the cases that we tested, it is true. All right, let's look at the last example. Try number 5. For each conjecture, test the conjecture with several more examples or find a counterexample to disprove it. Okay, part A says for every integer n, the value of n squared is positive. Is that true? If it's true, provide several more examples. If it's not, provide a counterexample. Part B, a number is divisible by 4 if the last 2 digits are divisible by 4. Is it true? If it's true, find more examples, and if it's not, find a counterexample. See if you can do it by yourself. Come back when you're ready for answers. Okay. Part A. Did you get it? Are you ready? Every integer n. Now, what is an integer? Okay. No fractions, no decimals, but a whole number. Does it include the negatives? Yes. Does it include 0? Yes. So, can we use 0 as a counterexample? Yes. Is 0 a positive number or a negative number? Neither. So can we use that? Yes. Yes, we can use 0. So all negatives and all positive integers will make n squared positive. But 0 is neither positive nor negative. So when n is equal to 0, 0 squared is 0, and 0 is neither negative nor positive. Okay, so if you figure that out, good. If you didn't, and you provided more examples, and that's like 50% right. Okay, for the conjectures, for the cases that you tested, it would be true. But for this case that you haven't tested, it's not true. Alright, part B. A number is divisible by 4 and the last 2 digits are divisible by 4. Is this true? Can you provide a counterexample? If you can, I would be surprised. But provide some examples, some more examples for that. So a number divisible by 4 is the first number that we want to figure out. Let's say 3016. Is that divisible? Is that divisible by 4? Yeah. And if the last 2 digits are divisible by 4, this divided by 4 is 754. And last two digits, so 16, is divisible by 4. And what is another example? 5,108. That's a big number. You don't have to use a big number, but you could. That's divisible by 4. The last 2 digits, 08, is divisible by 4. It is divisible by 4. And another example, 7,712 divided by 4 is 1,928. Yeah. And the last 2 digits, 12, is divisible by 4. So in all 3 cases tested so far, the conjecture is true for the 3 cases tested. Okay, so that's it for this lesson. Let's summarize our lesson. Inductive reasoning. So remember that inductive reasoning leads to a conjecture by observing patterns. It uses specific examples to make generalization. But it does not show that a conjecture is true. So conjecture could be disproven by a counterexample. Okay? So if you look at this diagram, from the pattern, you can generalize and make a conjecture. But you can test the conjecture to see if there's any counterexamples and see if all the cases will be true for that conjecture. Okay? So in order to prove the conjecture is wrong, provide a counterexample. But test all conjectures. They are not proven. All right, that was lesson 1-4, inductive reasoning. And so if you have any questions, please ask Ms. Kang. Otherwise, we'll continue lesson 5, conditional statements, in the next video. Thanks for watching. Bye.